A farmer has 1,556 feet of fencing available to enclose a rectangular area bordering on a river. No fencing is required along the river. Let X represent the length of the side of the rectangular enclosure that is perpendicular to the river. And we want to complete parts A through D. So we have a picture here of our river. And we're going to build this rectangular enclosure alongside the river. We don't need any fencing along this side of the river. And we're labeling X as the side that is perpendicular to the river. So perpendicular is at a 90-degree angle. And this side will be parallel to the river. So in part A, we want to create an expression that represents the side parallel to the river. So when we're trying to find this side, we can label the other side as X. And we want to find the length of this side here. I'll let this be Y. And if we go back to our problem, the farmer has 1,556 feet of fencing, and we know that he's using the fencing, he or she is using the fencing along these three sides. Now, the more fencing that you use, the larger area you can create. So we're going to use all of the fencing to create this rectangular enclosure. So we know that if we do X plus Y, the sum of those three sides, it'll equal the amount of fencing that we have. So that works out to be 2x plus y equals 1,556. I think I'm going to move over here to the side where I have some space. And my goal is to find an expression for this side. So I'm going to solve for that by subtracting 2x. That would give y equals 1,556 minus 2x. So that is the expression that we're going to use for this side. 1,556 minus 2x. So that's our answer to part A. So then we want to know what is the length of the side parallel to the river when the side perpendicular to the river is 389 feet. So remember, the side perpendicular to the river is labeled as X. So we're saying that X is 389, and we want to know the length of the side parallel to the river. That's what we labeled as Y. So 1,556 minus 2 times X, 2 times 389. I'll use my calculator to work that out. 1,556 minus 2 times 389 is going to give 778. So in the next part, and this is going to be in feet, and this would be in feet. So in that next part, we want to create a function, a of x, that describes the area of the rectangular enclosure as a function of x, where x is the length of the rectangular enclosure that is perpendicular to the river. So we know that area of a rectangle is going to be length times width. We have our width and length labeled, So we can do x times 1,556 minus 2x. And if I use the distributive property, I'll get an equation, 1,556x minus 2x squared. And now we have a function that represents the area of the function. So in our final part, we want to find the area of the rectangle when the side perpendicular to the river is 389 feet. So once again, this is x equals 389. And we can substitute this into our area function to get 1,556 times 389 minus 2 times 389 squared. We're going to type this in the calculator. Give me just a second to pull that calculator up. Let's make some space at the bottom here. Okay, so in our calculator, we're going to type the 1,556 times 389 minus 2 times 389 squared. And we get 302,642. And there is an easier way to get that area. If you'll remember, we have the width and the length from earlier, so we could also do area is equal to 778 times 389. And I just want to show you in the calculator that we get the same value. 778 times 389 gives us that 302,642. In this question, it says, let y equals f of x be the function sketched on the right. Use the graph to sketch the graph of y equals f of x plus 4 minus 6. Determine the 4 points on the new graph. So we're given this picture over here, and this picture is labeled as f of x. And our goal is to graph this new function f of x plus 4 minus 6. And we've been given a few questions to kind of help us sketch this new graph. If we look at our picture, we have some sort of key points on our picture that have been labeled for us. -4, 0, -2, 2, 0, 0, and 2, 2. And these questions ask us to find the location of this point on our new graph. And once we find the location of these points on our new graph, we'll be able to sketch our new graph. So when we look at this new equation, y equals f of x plus 4 minus 6, you can see that we are using f, so that's why we're going to be using this graph on the right to find our new graph. And then we notice that we have these changes to the equation. We have a plus 4 that's inside the function and a minus 6 that's outside the function. So these are transformations that are occurring onto our function. So we have a plus 4 and a minus 6. Now when we add and subtract to a function, this causes a shift in the graph. So we have adding and subtracting, we're going to have shift. Now, if that adding is on the inside, adding or subtracting is on the inside, it's a horizontal shift. And if that adding and subtracting is on the outside, it's a vertical shift. Now, horizontal is either left or right. Vertical is either up or down. So horizontal being either left or right, we're going to look at this plus sign. And because it's plus, we know that it's going to shift to the left. And then with vertical being up or down, this minus sign is going to tell us to shift down. Okay, now if this is information that you don't know, it's because you have to have this kind of stuff memorized. So let me just give you a quick glance at the information that you have to have memorized. And that's where I've gotten this from. Okay, so I'm going to kind of go off screen for a second here so you can see this picture. So this is all the information that you have to have memorized about the shifts to know which direction. If you're adding and subtracting is on the outside, it's a vertical shift. Plus is up, minus is down. If you have your adding or subtracting on the inside of the function, it's horizontal, and plus is to the left, minus is to the right. Okay, so that's where I got that information from, just some facts about transformations that I've memorized. So now that I know that I'm going to be shifting left 4 and down 6, I know what's going to happen to each one of these points. So if I move to the left 4, 1, 2, 3, 4, that is subtracting 4 from whatever the x coordinate is. And if I move down 6, that is subtracting 6 from whatever the y coordinate is. So on every one of these ordered pairs, I'm going to subtract 4 from the x and subtract 6 from the y to get to my new point on the graph, which is -8, -6 for that first one. So for every one of these, I'm going to subtract 4 to the x, subtract 6 to the y, and my new point for -2, 2 moves to -6, -4. I'm going to subtract 4 to the x of 0, 0, subtract 6 to the y of 0, 0, and we get to the point -4, -6. Our last one, 2, 2, we subtract 4 from the x, subtract 6 from the y, and that gets us to the point of -2, -4. So I'm going to erase these markings that I was doing for an example, and let's write our new points. So -8, and -6 would be here. -6, -4 would be here. -4 and -6 would be here. And -2 and -4 would be here. And I can sketch the graph. We have the semicircle here and a straight line here. So we've been able to take our graph and shift all of the points to the left 4 and down 6. On this question, it says, is the function 1-to-1? Use the horizontal line test. Okay, So I've added in this definition of what a one-to-one function is. A function f is one-to-one if for any values a not equal to b in the domain of f, f of a is not equal to f of b. So this is saying that if we have x values that are different, then our y values will be different. And so this is a test that we use to basically show if the y's are unique. Now the horizontal line test is how we decide whether that whether that graph is a one-to-one function. And the reason why we use a horizontal line is because if we think about the graph of a horizontal line, and we think about the ordered pairs that are on that horizontal line, all of the ordered pairs will have the y being the same. And so we want the y's to be different. The horizontal line has all the y's being the same. So it's a good comparison to our graph. The horizontal line is the opposite of what we're looking for. So on this graph, we're going to draw horizontal lines, and we're going to pay attention to the intersection points. And since these horizontal lines are intersecting the graph in only one point, we know that there's only one y value. Those y values are not repeating. All the y values are different. Now, it may be a little bit confusing if we focus in on this part of the graph, because it looks like the graph turns into, it looks like the graph turns into a horizontal line as we get closer and closer here. But this portion of the graph never turns into a horizontal line. There's always going to be a little bit of a gap in between this line and the x-axis. Even though we can't see it, if we were able to zoom into this, there would always be a little separation between the line and our graph. And so what's happening to the graph is it gets closer and closer. It never reaches it. So when we do the horizontal line test here, we're only crossing in one place. So in this particular example, this function is a one-to-one function. I've zoomed this way too big. Sorry about that, guys. So this function is one-to-one. A baseball player swings and hits a pop fly straight up into the air to the catcher. The height of the baseball in meters t seconds after it was hit is given by the quadratic function h of t equals negative 4.9 t squared plus 14.7 t plus 1. How long does it take for the baseball to reach its maximum height? What is the maximum height obtained by the baseball? So in this question, there's definitely some keywords that we want to pay attention to. In the question, it's asking us to find the maximum height. And what we also notice is that the function that measures the height is a quadratic function. And we know that the graph of a quadratic function is going to be a parabola. Looking at this leading coefficient of a being negative 4.9, we know that that graph of the quadratic function is going to be a down-facing parabola. So when we're looking for this maximum height, we know that that maximum height is going to occur at the vertex of that parabola. So when we solve this question, we're going to be focused on finding the vertex of that quadratic, and it will tell us what that maximum height is. So we've got our function h of t equals negative 4.9 t squared plus 14.7 t plus 1. We have a formula for finding the vertex, and that formula for the vertex is usually labeled as hk. And I know that's a little bit confusing because this is labeled as an h. So let's just keep in mind that that is h representing height. And the h that we're using right here, this is representing the x of the vertex, the x-coordinate of the vertex. So the formula for h is negative b over 2a. And then we're going to find the k part by substituting that into our height function. So this h is the h of the vertex, this h is the height of the function. So in our example, a is negative 4.9, b is 14.7, and c is equal to 1. We're going to substitute those in for the vertex formula. Negative b, that's negative 14.7, over 2 times a, that's 2 times negative 4.9. We're going to use our calculator to work that out for us. We've got negative 14.7 divided by, and I have more than one thing in the denominator, so I'm going to make sure to put parentheses around the denominator. 2 times negative 4.9, and we get 1.5. Now remember, this h is the x-coordinate of the vertex. Now we're going to find k, which is the y-coordinate of the vertex, and we're going to substitute this 1.5 into our height function. That's negative 4.9 times 1.5 squared plus 14.7 times 1.5 plus 1. Okay, so let's put that in our calculator. So we have negative 4.9 times 1.5 squared plus 14.7 times 1.5 plus 1. So we end up getting 12.025. And this is going to be the height of the ball. And the height is in meters. So we're going to get our maximum height of 12.025 meters at a time of 1.5 seconds. We have for the pair of functions to find f plus g, f minus g, f times g, and f over g. Give the domain of each. So we're given our f of x. We're given our f of x to be x squared minus 1, and our g of x to be 5x plus 20. So we are going to find f plus g of x. That's going to be f of x plus g of x. That's x squared minus 1 plus 5x plus 20. And we're just going to combine like terms to get x squared plus 5x plus 19. And we've just found our function f plus g. And we're going to find f minus g of x. That's f of x minus g of x. You have to be a little bit more careful with subtraction because we want to make sure that we're subtracting the whole function. So f of x is x squared minus 1. We're going to subtract g of x. I'm putting parentheses around g of x. That's 5x plus 20. We have x squared minus 1 minus 5x minus 20. And we'll combine like terms to get x squared minus 5x, and then negative 1 and the negative 20 combine to be negative 21. So then we're going to multiply, that's f times g, by doing f of x times g of x. F of x is x squared minus 1, and g of x is 5x plus 1 plus 20, and we want to multiply them. So once again, we have to be careful here because we want to multiply all of f by all of g, so we're going to put parentheses so that we multiply all of it and also that it represents multiplication. So when we multiply, we're going to do x squared times 5x, that's 5x cubed. X squared times 20 is going to give me 20x squared. Negative 1 times 5x, it's a minus 5x, and negative 1 times 20 is a minus 20. We don't have any like terms there, and so we won't combine them. So then finally, we're going to find f over g of x. So we're going to put f of x in the numerator and g of x in our denominator. F of x is x squared minus 1, and g of x is 5x plus 20. When we simplify these fractions, we want to make sure that we're reducing it to lowest terms, canceling out any common factors we might have. Our numerator is a difference of squares and can be factored into x plus 1, x minus 1. And our denominator has a greatest common factor of 5. If we factor that out, we get x plus 4. And there are no common factors here, so our rational function is in lowest terms, f over g. We want to come back here and find the domain of each one of these functions. And when we're finding the domain of functions that we add, subtract, multiply, and divide, we have to first consider the original domain. Because if we're using these functions to put together the new functions, we have to have, at the very least, the same restrictions. So both of these functions are polynomial functions, and polynomial functions have a domain of all real numbers, negative infinity to infinity. So the domain of f will be negative infinity to infinity. The domain of g will be negative infinity to infinity. So when we add, subtract, or multiply, because we're having polynomials, they create polynomials. So if you have two polynomials and you add, subtract, or multiply them, you're going to get a polynomial. So all of these new functions have a domain. I'm going to say domain of f plus g is also all real numbers because these are polynomial functions. Domain of f times g is negative infinity to infinity. And domain of f minus g is negative infinity to infinity. Now the division is different. Now when you introduce division, you have now created something that is not a polynomial. This is a rational function. And with rational functions, our denominator cannot be 0. So we're not going to have a domain of all real numbers for the division. We need to take the expression in the denominator, which is our g of x in this example, and set it equal to 0. And we solve, we get 5x equals negative 20, divide by 5, and we get x equals negative 4. That negative 4 is a restricted value because it's going to cause the denominator to equal 0. So our domain here will be everything, all real numbers except for negative 4. And we write that in interval notation. Let me zoom out so I'm not losing part of my question here. Our interval notation will be negative infinity to negative 4, union with negative 4 to infinity. And that's the domain of f over g. Find f plus g, f minus g, f times g, and f over g. Determine the domain for each function. F of x equals square root x, and g of x equals x plus 4. So we want to find these combined functions, f plus g, f minus g, f times g, and f over g, and then also find the domain for each one of those. So to find f plus g of x, we're going to take f of x and add g of x. F of x is square root x, g of x is x plus 4, and there are no like terms here, so this is how we would write our answer, square root of x plus x plus 4. Then with f minus g, we're going to do f of x minus g of x. And with subtraction, we're going to be more careful. We want to make sure that we're subtracting the whole function g of x, so we'll put parentheses around that. That's square root x minus x plus 4. So we put parentheses around all of g of x so we could subtract all of it. We'll distribute that negative, so we get negative x minus 4. And there are no like terms here. So we've got our function f minus g of x to be square root of x minus 4. So then we're going to do multiplication, f times g of x. That's f of x times g of x, square root x times x plus 4. You'll notice I put parentheses here as well. And that's because we want to make sure that we're multiplying by all of g of x If f of x had more than one term, we would also put parentheses around f of x. So we have square root of x times x plus 4. We could use the distributive property and write this as x square root of x plus 4 square root of x. And we have our f times g. And then f over g of x, we're going to put our f of x in the numerator and our g of x in the denominator. F of x is square root x. G of x is x plus 4. And I wouldn't do any simplification to this. There are no common factors. So we have f over g of x being square root of x over x plus 4. We don't want to forget about this second part when we're finding the domain. When we find the domain of combined functions, you have to consider the domain of the individual functions. So we used square root of x to create it. The domain of square root of x is going to be x needs to be greater than or equal to 0, because the square root of negative numbers would give you imaginary. So let me give myself a little bit more space there. So for f of x, which is square root of x, the x needs to be greater than or equal to 0, and if I were to write the domain of f, it would go from 0 to infinity. For g of x is a polynomial, and it doesn't have any restrictions on x, so the domain of g is going to be from negative infinity to infinity. When we use f and g to create that, now we need to bring in the restrictions from those originating functions. And we only have this restriction of x being greater than or equal to 0. So for f plus g, the domain of f plus g, we only need to consider that restriction for 0 to infinity. The same thing happens with subtraction, and the same thing happens with multiplication. However, with division, because we're dividing, we have to make sure that denominator is not equal to 0. So with division, we get this extra restriction that the denominator cannot equal 0. So if we subtract 4, we get x is equal to negative 4. That's an extra restriction. However, for this example, if you consider the two restrictions we have, x being greater than or equal to 0 and x cannot equal negative 4, this statement already covers that statement. By x being greater than or equal to 0, we know that x is not equal to negative 4 because it can only be positives or 0. So our domain for f over g will also be 0 to infinity. But let's consider for just a second here, what if this wasn't an x plus 4? What if it was a minus 4? If it was x minus 4, we would add 4, and now we have this extra restriction that x cannot equal 4. So what I'm talking about right here is hypothetical. So if our f was still square root of x, but our g was x minus 4. So in this hypothetical scenario, our restrictions are that x is greater than or equal to 0 and x cannot equal 4, so if x needs to be greater than 0 and not equal to 4, we have to exclude 4, but include everything else that's greater than 0, we would get a domain of f over g to be 0 to 4 union with 4 to infinity. So these are all the numbers that are greater than 0 except for 4, greater than or equal to 0 except for 4. Let me zoom out so you can see the whole thing. And remember down here, this is our hypothetical example. We want to rewrite the quadratic function in vertex form using completing the square. And then in parts A through C, we want to find the vertex, the orientation of the graph, and the axis of symmetry. The function that we're working with is f of x equals 2x squared plus 4x minus 5. And we want to use completing the square to write this in that vertex form. So we're going to start off with our function 2x squared plus 4x minus 5. And we want to factor out this coefficient of 2, but we're only going to factor it out of the x terms. So if I factor out a 2, I'll be left with x squared plus 2x, and I'll carry down that minus 5. I'm going to rewrite this, leaving a little bit of space inside the parentheses. And I'm leaving a little bit of space inside the parentheses for the completing the square process. So on the side over here, I'm going to calculate what I like to call the magic number. And that magic number is going to make the completing the square process work. So to find that magic number, you're going to start with the coefficient on the x. So you start with that 2. You're going to cut it in half and square it. 2 over 2 is 1. 1 squared is 1. So the magic number for this is 1. So putting a 1, a plus 1, in that blank is going to make x squared plus 2x plus 1 factor into a perfect square. But I'm not allowed to just put any plus 1 into the equation without balancing it out. So the way that I balance it out is by figuring out how to do the opposite of what I've just done. And it's a little bit confusing because it's inside this parenthesis here. Because it's inside the parenthesis, I also have to consider this number out here. So what I'll do is I'll multiply these two numbers together. 2 times 1 is 2. And then to balance the equation out, I need to do the opposite on the end here. So the opposite of 2, a positive 2, would be a minus 2. So that minus 2 balances out writing the 1 in the parenthesis. So now that I have the magic number and the equation balanced, I'm going to be able to factor what's inside the parentheses. That's going to factor to be x plus 1 times x plus 1. And then negative 5 and negative 2 combine to be negative 7. And like I said earlier, not only did this factor, it factored to be a perfect square. X plus 1 times x plus 1 is x plus 1 squared. So I've rewritten this function into the vertex form. And now that it's in the vertex form, I can identify the vertex. So in part A, the vertex is going to be -1, -7. The orientation of this can be found with the value of A, either in either form. A is 2, which is a positive number. So the orientation of this is an up-facing parabola. The graph will be up-facing like this. And then finally, the axis of symmetry. The axis of symmetry is going to be a vertical line that passes through the vertex. And because it passes through the vertex, we're going to use the x-coordinate from the vertex to write the equation of that vertical line. So it's going to be x equals -1 for the axis of symmetry. A rancher has 5,334 feet of fencing available to enclose a rectangular area bordering a river. She wants to use part of the fencing to create a partition to separate her cows from her horses by dividing the enclosure into 2 equal areas, as shown in the figure to the right. No fencing is required along the river. Let X represent the length of the center partition and complete parts A through D. So we have a nice picture of what's going on here. We have a river. The rancher is building these rectangular pastures bordering along the river, and she's creating them with this little divider called a partition in the middle. And that's so she can separate the cows and the horses. It also says to let X be that center partition. And that's the variable that's going to be used throughout. Now we want to create an expression that represents the length of the side of the fence that's parallel to the river. So that's this part right here. The length of fence that's parallel to the river, let's call that Y. Then we want to find the length of the side of the fence parallel to the river. If that center partition is 889. So they're going to give us a value of X, and we're expected to find the length of this fence here. We want to create a function that represents area. So it describes the area of these 2 pastures as a function of X. And then finally, we're going to find the area when that center partition is 889. So when we are trying to do this part A, which is to find the length of this side here, we are going to use something that is similar to perimeter. Now we have perimeter formulas for rectangles, but this has a little bit extra to consider because we're not going to use the side along the river. So we're using these sides as well as the side parallel to the river, and we have this extra partition. So we're using perimeter, but we're going to have to modify it because we're not using the river side and we have this extra side in the middle, that middle partition. So if we use the fact that these are rectangles, I know that this is also X and this is also X. So we have 3 sides that are X and 1 side that is Y. And those sides are where the fencing is going to go. So I know that that is going to equal, the sum of those will equal 5,334. I can solve for y in terms of x by subtracting 3x on both sides. I have y equals 5,334 minus 3x. And this is the expression that represents the side that's parallel to the river. Then if we want to find the length of that side, when we're given that the center partition is 889, we're given that value of x, we can substitute to get the value of y, the side parallel to the river. It's going to be 5,334 minus 3 times 889. We can do that with our calculator. So that's 5,334 minus 3 times 889, and that gives 2,667. And the units that we're using in this problem, let's see, are feet. So that's 2,667 feet. But then we want to create a function that represents area, the area of these two enclosures. So if we're finding the area, we're going to find the area of this big one here. And we can use our normal area formula, which is length times width. So our area function will be x times y, length times width, but we had an expression for y from part A. So that's x times 5,334 minus 3x. And we can use the distributive property to write this as 5,334x minus 3x squared. So now we have a function that represents the area of those enclosures. And then the last part here, we're now given that the center partition is 889 feet, and we want to know the area, so we can substitute that into our area function. Area of 889, that's going to be 5,334 times 889 minus 3 times 889 squared. So we'll use our calculator again to work that out. That's 5,334 times 889 minus 3 times 889 squared. And it looks like a really big number there. That's 2,370,963. And the units there would be square feet. Now there is a simpler way to get that value. We have the length and width here that we could just multiply together as well to get the area. So 889 times 2,667, let's see that in the calculator. So 889 times 2,667 also gives us that 2,370,963. So I wrote this backwards. So we get 2,370,963 square feet. Thank you for checking out my videos. Have a great day.